Hi everyone, this is Ms. Segovia. I'm going to work you through the Hardy-Weinberg practice problems. So to start with, let's review our equations. We have P plus Q equals 1, and P squared plus 2PQ plus Q squared is also equal to 1. When you look at these, you can think of them in terms of our alleles, whereas our P would be equivalent to our dominant allele, and our Q would be our recessive allele. And so our first equation is just looking at the frequency that each of those occurs in the population. Over here though, P squared, if we take two of these, we're looking at our homozygous dominant genotype. PQ would be our heterozygous genotype, and Q squared would be our homozygous recessive genotype. So this is really helpful when you're reading the problems to kind of think about in terms of the alleles. Are we looking at the genotype or just the allele? Speaking of which, right here, the recessive genotype is our small a, which in our equations case is Q squared. And this is the one that's going to be your go-to, because whenever you find out what the recessive genotype, the only option for it is to be our homozygous recessive little a. If they ever give you the dominant genotype, then we could actually be either our homozygous dominant or the heterozygous, because we don't know visually, just looking at the creature, whether it possesses this genotype or this genotype. But if we see the recessive phenotype, we know it must be the recessive genotype. And that is really, really handy as we work Hardy-Weinberg. So likewise, if they're asking for the recessive allele, then they just want to know our little a, which is our Q value. So it's important to pay attention in the problem if they're giving you genotype or allele information, as that'll affect your outcomes. So in our first problem, in Drosophila, the allele for normal length wings is dominant over the allele for vestigial wings. Vestigial wings are stubby little curls that cannot be used for flight. In a population of 1,000 individuals, so let's just take a note of what they've given us, we see 360 show the recessive phenotype. So the recessive phenotype is our visual, so that means they must be little a is equal to 360. How many individuals would you expect to be homozygous dominant and heterozygous for the trait? So we're looking for homozygous dominant in our answer and heterozygous, two answers being given for this problem. So let's see what we have. They've given us the little a value as 360 in a population of 1,000. Whenever we work with Hardy-Weinberg, we also always want to work with the frequency, not the raw numbers. So the frequency of the little a in this population would be taking, so let's just do a little note. So the frequency of little a is equal to taking our 360 and dividing it by 1,000. And once we do that, we'll see the frequency is 0.36, little a. Now, if you recall from our main equations, little a is the equivalent of Q squared. So we can add that our Q squared value is equal to 0.36. Now, in our equations, if we want to solve for what this and this is, we need to know what the p-value. And so to find our p-value, we can use our first equation, which is p plus q equals 1. We have the q squared value, so to get the q value, we just need to take the square root of both q squared and 0.36. So our q is equal to 0.6. Now I know the temptation is to go 0.06, because thinking that 6 times 6 is 36, but we're working with decimals here. Don't be afraid to double check your math using your handy dandy calculator. And just to verify that, we have 0.36 square root is 0.6. So be mindful. So now we have our Q value. So if we apply it to our formula P plus Q equals 1, we could see that P plus 0.6 equals 1, which means that P must be equal to 0.4. So once you have a Q value and a P value, the rest of this is actually pretty simple. So to find our homozygous dominant, that's big A, we do P squared. So we have 0.4. So So we're just going to kind of box this off a little bit because we're getting a little too much information here. So to get homozygous dominant is our p² value. So that's going to be our 0.4 squared. And so 0.4 squared is equal to 0.16. Now, as much fun as it would be to stop there, actually, I'm sorry, p² value is 0.16. As much fun as it would be to stop there, the question wasn't asking us for the frequency of the homozygous dominant. It wanted to know how many individuals. So now that we have our 0.16, to get our individuals, we need to multiply that by our population size. So we're going to take our population of 1,000 times 0.16, and we get 160. And so just to shorthand it a little bit, we have 160 homozygous dominant in our population. The question also wants to know heterozygous. So I'm just going to box this off a little bit here. That is up here, heterozygous is 2pq. So we're going to take 2pq, so that's going to be 2 times 0.6 times 0.4, which is going to be equal to 0.48, which means that our population has a frequency of 0.48. So let's find out how many individuals. We're going to take 1,000 times 0.48, and that is 480. So our final answer here is 480 heterozygous individuals in the population. Now, just to do a little fact check and make sure you've done it correctly, it's really helpful to add up your p², 2pq, and q² values to ensure that they equal 1. So in this particular case, just to check, we're going to take our 160, that is our big A, plus our heterozygous, which is 480, plus our homozygous recessive, and that was given to us in the problem, and that's 360. And when you add those all up, you get 1,000. And that means that you did it correctly. So our final answer here is 160 homozygous dominant and 480 heterozygous. This video is getting a little long, so I'm going to stop. I'll post the other ones, and you can go click them and check your answers.